my younger brother. He's a sociology professor, and he's now with the Hebrew University of Jerusalem. He's now in sabbatical in Hong Kong. And he is a sociologist, and he trusts me to give him weather predictions. And he said they are talking about another typhoon coming to Hong Kong. And so I looked at this forecast, and sure enough, there is a typhoon, a big one coming. This is how it looks. So coming to Taiwan tomorrow, and on Friday, maybe reaching Hong Kong. And of course, a lot of lightning, a lot of rain. He's worried a little bit. I told him, don't worry, it will not be as strong. You see, category 3, but after reaching Taiwan towards China, maybe just category 1, not that bad, but still very strong. I mean, a lot of rain. A lot of rain. He said last time they had cancelled all classes in the university. There was a big flooding event, and so, yes, I'm kind of always looking, and you know, it's a fascinating age that we live in, that you can get on your mobile phone, anywhere you are, global data on the atmosphere. That's amazing. I think your generation was born digital, okay? We are called migrants because we were born analog, my generation. Analog. My first Fortran program was on punch card with a pencil on paper, like that. Crazy. And look at what we have today. The memory that you have here on such a smartphone is larger than the combined memory of all American and Soviet spacecraft that were launched until 1995. So this is amazing what we have. I think it's a beautiful age, but for me it's kind of, you know, there's a famous quote by Albert Einstein, or so they say, that modern technology is so sophisticated that it can easily be perceived as magic. Because we don't know what's going on. It's just a box that we punch and we get what we want. It's like magic. Anyway, let's get back to our atmosphere. And you may have seen during the break that we have now a WhatsApp group. So as I said, please just introduce yourself. Don't be shy. And we will use this for communication. I will upload all the presentations as PDF format after class to the WhatsApp group. And we have, maybe tomorrow, I'll try and give you some data and see if the file is not too large, then we will use the WhatsApp group. But if it's too large, we'll figure out a way, maybe by email, to send someone and to share the data so that you can actually work on the analysis. I have 2 assignments that are related to data analytics and 1 related to creativity, free creativity, which I wish you to come up with, but that's for Thursday. Okay, so we live at the bottom of an ocean, but it's an ocean of air. And we are at the bottom of the ocean. And the air gets thinner as we go up. And the traditional boundary where the atmosphere is bordering with outer space is 100 kilometers. That's the formal definition of where the atmosphere ends and space begins. Okay? Basic knowledge. Why is it so important, this definition? Any idea? Comes from politics. It's the sovereign airspace of a country until 100 kilometers. So if anybody enters your sovereign airspace below this altitude, he infringes on your country's sovereign, and you are allowed to shoot him down or, do something. But above 100 kilometers, everybody can fly anywhere. This is why satellites don't need permission, because they are in space, they're above. So the airspace stops at 100 kilometers. And why this number particularly? It's not just because it's a nice round number. It's because you cannot fly with an airplane with aerodynamics. There's not enough lift because the air is so thin that you cannot fly aerodynamic flight at this altitude. You need to have orbital or suborbital velocity, and this is what distinguishes between an airplane and a spacecraft. So this is the definition. It's called the von Karman line, based on the physics of von Karman, a German physicist, who calculated the exact density of the air at 100 kilometers and deduced that you cannot fly a flying object based on the lift it creates through its speed, and you have to have an orbital speed. By the way, that's what you should know. This altitude also has a symbolic meaning, because if you go to astronaut school and you get to fly to space, then you are allowed to wear the golden astronaut wings, okay? If you pass this altitude, 100 kilometers. If you never flew above 100 kilometers, you have silver astronaut wings. So you graduate from astronaut school and you've never been to space, silver. You fly above 100, gold. Okay, symbolic but very important to people. And you know that now you have those private companies like Virgin Galactic, SpaceX, and Jeff Bezos flying people to space. If you pay enough money, you can be an astronaut. Sort of astronaut. And, just do ballistic. Being launched, 100 kilometers, you go down, you get the golden wings with no training. That's a fun. But anyway, so 100 kilometers. And in those 100 kilometers, the atmosphere is divided to certain layers. We live at the most bottom layer, which is the troposphere, 15 kilometers. All the weather, all the clouds, all the storms, all the rain, everything that is interesting occurs in the bottom 12 or 15 kilometers in the troposphere. Above it, we are in the stratosphere, that's the ozone layer, and then we go into the mesosphere and above. Of course, there is air above 100 kilometers, but it's really thin, diluted, and you can find molecules of the air up until the exosphere, 1,000 kilometers, where you have the polar lights, the aurora, and other electromagnetic phenomena. But this is, I would call, a remnant of the atmosphere. Most of the atmosphere, 90% of the mass of the atmosphere is in the lowest 15 kilometers. Okay? So, take-home message. 100 kilometer boundary between air and space, but most of the atmosphere is really below. And this is another schematic. Temperature decreases in the troposphere until the tropopause, and then rises again in the stratosphere because the ozone production and destruction are exothermic processes. So they emit heat, which causes the temperature to rise again until 50 kilometers, and then the concentration of ozone is so small that not significant, and the atmosphere gets cooler in the mesosphere, above 100 kilometers in the outer atmosphere, in the exosphere. So it's not temperature per se, it's energy of the atoms of the air. So this is the vertical profile of the temperature. And you know density decreases very, very fast. You cannot breathe above 5 or 6 kilometers. You need oxygen masks. So people who go to the Himalaya and climb mountains always need aid, because the partial pressure of oxygen is so low that you cannot sustain life without additional oxygen. So the total amount of air is very low. It's not that the percent of oxygen changes. It still remains the same, but because the total pressure, the total number of molecules is so low, not enough to sustain life on its own, so you need oxygen masks. How do we know this? So we use balloons. This is me some years ago doing balloon measurements. Let me show you, I hope this movie works. We did an experiment to measure certain electrical parameters of the atmosphere on Earth in several places at the same time. In Israel, in Russia, in Spain, and in Antarctica. Coordinated balloon launches. Coordination was not very successful, but I'll show you how we launched the balloon. I hope it is okay. Okay. Very short video, but pay attention. So we attached a GoPro camera to the balloon and launched it. Balloon does this rotational movement. Don't feel dizzy. Got stuck somehow. I don't know why it stopped. Anyway, kind of buffering the YouTube video. I'll stop it. But we reached 25 kilometers during this flight, and the balloon has a transmitter, so continuously data is being registered with this antenna. So we can get the temperature, humidity, pressure, and ionization rate. That was important to us. I will show you later. And this is how you build a profile with altitude. And then at a certain altitude, the balloon is expanding because the outer pressure is decreasing. It gets larger and larger, and then it explodes. And we had a parachute. So the payload parachutes down, and it has a beacon with a GPS unit, so it tells us where it's located, and we just go there and pick it up. For Spain, that was easy because it landed not so far from the launch site, so we picked it up. But here in Israel, we are surrounded by enemy countries. So it was drifting east towards Jordan and Iraq, and when the balloon exploded, it landed in the desert, very far. We could not retrieve it. So we lost the camera, we lost the payload, everything is lost. Anyway, this is how we build a vertical profile. By the way, you should know that meteorological services all around the world launch balloons twice a day, thousands of balloons, in order to create a vertical profile, and this data is collected and shared among all the meteorological services in the world, because this data is used for weather models, weather forecast models use this vertical profile as initial conditions for the models, and then they can predict what the weather will be tomorrow, the day after tomorrow, and through the weekend. Okay? And you know this already, that as we go up, temperature decreases because the air is thinner, so it does not absorb that much heat. And as I said, you cannot climb up without an oxygen mask. Okay, so that was the first part of my intro on the beginning, on the structure of the atmosphere and how it was created, and with some hints about the origin of life, which we will revisit. Now I'd like to talk about clouds. So this is from the seashore near Tel Aviv. You can see kites, people doing sports. What are clouds made of? What are clouds? Water, yes, but? Water in all three phases. Water vapor, liquid as drops, and snow crystals, ice crystals. Okay? So they are made of billions and trillions of small particles that are continuously generated and evaporated. Under certain conditions, they can produce precipitation and produce lightning, as we shall see. And the life of a cloud is on the order of an hour, a certain cloud, as an entity. Because after an hour, it would have changed and remorphed, either dissipated or regenerated as a new cloud. Okay? So there is an exchange of material, energy, and mass continuously in clouds, and the ingredients are, of course, water vapor and condensation nuclei and freezing nuclei. So basic meteorological definitions are that a cloud has a bottom, like we call it cloud base, the lower layer of the cloud, and the upper layer is the cloud top. And in between we have the cloud body, what usually when you kind of draw a cloud, this is the shape you usually draw. And there are two types of clouds: stratiform, shaped like a layer, or cumuliform, shaped like a heap. Okay? And this is the basic cloud atlas. It originated in the 19th century. And you know why? For practical reasons. Because back then, naval ships needed forecasts in order to know when a storm is coming. And the only way to predict storms was to view the shape of clouds, because people knew that certain clouds appear before a storm. And they call it mariner's wisdom, like ancient sayings. Clouds are red, sailors should take care, because there's a certain type of cloud that appears a day or two before a typhoon or a cyclone arrives. So there was a need to kind of organize all this knowledge into what we call scientific categories, such that in the 19th century, people were trying to categorize and organize nature. Okay? It's the beginning of botany, of geology. Everything was supposed to find an order and some rules of nature, the natural laws. And so that definition differentiated between three types of clouds. Stratiform-like, that look like layers. Cumuliform clouds, that look like piles. And rain clouds, that produce rain and precipitation. So this is the basic three categories, and subdivision of this category is the altitude of cloud base above the ground. Okay? If it's low, then there's just stratus clouds. If it's middle, between 6,000 and 20,000 feet, like 2 kilometers until 6 kilometers above the ground, it's called alto cumulus or alto stratus clouds. If it's very high, then it's called cirrus clouds, like a feather or like sheep. Different shapes, different altitudes, different physical properties, and clouds play a massive role in regulating Earth temperature because they reflect so much of the solar light back into space. So if you have a lot of clouds, more radiation is being reflected back to space, and probably less radiation reaches the ground, and so the temperature would be cooler in principle. And you may have heard the term geoengineering. I always come back to climate change because people are starting to lose hope that we will ever solve this problem. So they go to the radical extreme of saying, okay, we cannot fix it by regulating energy production, by transferring to green economy. Let's do something radical. Let's start playing with clouds. Maybe we can change the color of clouds. Maybe we can produce clouds where there are no clouds to begin with in order to reflect more radiation back to space, and by this we will cool the planet. It may seem to you like a radical idea, but actually we are already doing this inadvertently. I will show you. Inadvertently, we're changing clouds already. Clouds over cities, clouds over the oceans. But now people that propose geoengineering are advocating that we'll do this on purpose. A big debate in science. Big debate. Should we do it? Are we absolutely sure we can anticipate how each type of cloud will respond if we interfere with the physics? By, for example, spreading salt into the cloud, silver iodide. What will it do to the amount of rain? What will it do to the overall meteorological regime if we change the physics of clouds? So at the moment, it's put on the shelf. People say, okay, we will not start playing on a large scale with clouds. But slowly, slowly, I see this in the literature already. People are saying, okay, we will not do this, but let's simulate in a computer model what would happen if we do it. And they start running the models with different assumptions that if we change clouds, we may actually fight climate change very effectively and very quickly. But of course, there's a huge complication that involves the fact that clouds are not stationary, and that if you play around with toys in one part of the planet, you may affect parts that are not in your country. You may affect other countries. So international law, big complications. Are you allowed to play with the weather in your country and maybe affect the weather in other countries? So we're not there yet. So this is just a technical kind of slide that tells you the names of the clouds, the altitude of where they lie in the atmosphere, and whether they have precipitation or not. It will be in the presentation for you later. So the secret of making clouds. No secret, actually, but it took a while to understand. And there's a big message hidden in the physics of cloud production. You need humidity. We have enough of that here in Mumbai. You have cloud condensation nuclei. We have plenty of those in the air every day. But you need to reach saturation in order to create a cloud. And this is the secret. You need to cool the air to a certain temperature so that the water vapor will start to condense and create drops. This is basic geography, I think, undergraduate level, but people always sometimes kind of forget that the fact that you have humidity and you have condensation nuclei for the drops to form are not enough by themselves. You need cooling, and cooling usually in the atmosphere arises from vertical motion of the air. If you lift the air, it expands because the pressure decreases, and adiabatic expansion leads to cooling, and that's how you reach saturation. This is how clouds form in nature. Now, clouds are formed around cloud condensation nuclei. They are very tiny aerosol particles, I will show you. And a typical cloud is composed of what we call cloud droplets. They are 10 microns in diameter, in radius, very small, but very numerous. So there are 1 million of cloud droplets in any cubic centimeter of cloud air. So when you drive, when you fly through a cloud, you do not see them with your eyes. They are too tiny, but we can actually measure them. And when I was a PhD student, I did my PhD on cloud physics, this is what I was doing. I was flying with an airplane into clouds, I will show you, and measuring the number, concentration of cloud particles and of ice. And in order to kind of understand the cloud physics and whether those clouds are good for cloud seeding. I will explain why cloud seeding is important. So, typical cloud droplet, very small. Typical rain cloud is much larger, 1,000 microns. That's 1 millimeter in size, typical. So, from 10 micron to 1,000 microns, that's 100 times larger in radius, but in volume, that's 100 to the third power. Okay, that's 1 million, and that's 1 million times larger. In order to produce from cloud droplets 1 raindrop, you need millions of small droplets to coagulate and merge with each other. And that's a very slow process in the atmosphere. So many clouds are formed but are unable to produce rain. So like this morning, when I was waiting outside the hotel, so I saw many clouds, but they will not rain. There will not be rain today, not enough cloud droplets, and the air does not allow them to grow deep enough such that there will be enough collisions to create rain. During monsoon, no problem, you will have as much rain as you want. So where do those cloud condensation particles come from? They come from everywhere. Everywhere. The trees, the dust, the pollution, smoke from chimneys, exhaust from cars, the paint from buildings peeling down, all those particles, and from the sea, of course, sea salt from the Arabian Sea, all those create huge amounts of solid particles that can be good as condensation nuclei to produce cloud droplets. Okay? And we have no shortage of those particles. However, not all those particles are good or are optimal to produce cloud droplets. And so there is sometimes a necessity to maybe add more particles in order to expedite the production of rain. And this project has been going on in Israel from the 1950s because the leaders of the country understood that we are on the border of a desert. We will not have enough water to sustain the economy and the growing population. So back in the 1950s, two projects started: desalination and cloud seeding. And Israel tried to do this with many techniques, dubious results. I'm not sure we succeeded in getting much more rain, but even a little addition of water is important to a desert country. And so we used to go with airplanes. We have a lot of desert dust, but that's not enough. That's not enough to produce what we need. And now countries in the Persian Gulf, like Qatar, Abu Dhabi, Dubai, they also want to start revisiting the idea of cloud seeding. Maybe we can produce more rain. Okay? So I'm not sure it's possible. It's a big debate in science, and there are many, many reports and numerous papers that I will share with you if you're interested. Is cloud seeding even effective? Can we actually measure the additional water? Because you surely understand as scientists that you always have to have an experiment and a control group, right? So you have a cloud that you don't touch, this is the control, and then you have a cloud that you interfere and you put stuff in the cloud, and then you compare the rain from this cloud and the rain from that cloud, right? But there are no two identical clouds in nature. So you cannot actually say that I increased the amount of rain by such and such amounts. So we did statistical experiments for many, many decades, and still the results are inconclusive. But lately, because droughts are becoming more and more severe, many nations are coming back to those ideas that were actually kind of shelved in the 1990s, and people stopped doing that. And now rain enhancement is coming back. You can look in Google Scholar and see how many mentions of rain enhancement. It's like this, and then a minimum, and now it comes back. Because desperate times require desperate measures. People are in need of water. One of the most abundant particles come from organic sources. Either volatile organic compounds, which I'm sure you know what are they, that are emitted and condensed by plants and vegetation, or through biomass burning. You have the smoke coming up into the air. We call it the brown sugar kind of mixture of organic alcohol, VOCs. They produce those complex forms of cloud condensation nuclei, which eventually turn clouds and produce clouds, but not always efficient. Research shows that sometimes even pollen particles, bacteria, viruses, fungi, and algae are good in producing aerosol particles, some of which are good for creating clouds. Okay? And in the 1980s, my thesis advisor at the university, Tel Aviv University, where I did my PhD, they discovered a specific type of bacteria that was extremely efficient in producing clouds. They did in a cloud chamber in the laboratory, okay? And they showed it and published a paper that this type of bacteria can produce clouds quite easily. However, you can imagine that no one approved large-scale atmospheric experiments seeding with bacteria. Everybody was very afraid to release either live bacteria or just the proteins that make the bacterial DNA into the atmosphere. Kind of, this apprehension from biological weapons and biological and contamination back in the 70s or 80s. So we cannot say that that was proven in the air, but in the lab, we know those materials are actually acting as cloud condensation nuclei. Many publications that show that they exist in the air, in the open air, and are good in creating cloud droplets. And of course, the best and foremost, most abundant cloud condensation nuclei come from the sea. It's sea salt, sea spray, from the evaporation of droplets that are created on the crests of the waves of the ocean. Waves break on the shore, the sea spray evaporates, and you have salt suspended in the air to be reabsorbed into the developing clouds and produce again cloud droplets. This is what we call the water cycle in nature. Okay? Evaporation from the sea, condensation again, coming back as rain, going back to the sea, or evaporates through evapotranspiration from plants. So you know this basic thermodynamics. Saturation is when we have the exact equilibrium between what is being evaporated and what is being condensed. And when we have supersaturation, when we have clouds that develop and cool rapidly, we have much more condensation, and then we have rapid growth of cloud droplets such that we can produce large drops. And if the temperature is low enough, we can produce ice. And ice is the secret ingredient that is needed to produce lightning. But that is like a spoiler alert to something I will teach you later. Okay, I was debating, should I go into, very quantitative, formula-based kind of course? And after consulting with Varsha, I decided I will keep it descriptive, but I could not help myself. There's one equation I need you to remember. I think it's the most important equation in the discussions today of climate change and what is happening to the atmosphere. It's called the Clausius-Clapeyron equation, and it describes the saturation water vapor pressure as a function of temperature. In plain words, it shows how much water vapor the air at a certain temperature can contain before it starts to condense. Okay? And the basic equation tells you that the warmer the air gets, the more water vapor it can contain. Hotter air contains more water vapor. Okay? So temperature increases, evaporation increases as well, but the air does not reach saturation because it contains more and more vapor. And then, if we induce an upward motion and start cooling the air, we get much more water coming back to the liquid phase. Okay? And this is why we see more and more evidence, and this is plain to see. Like, just look at the news from last week in New York City, in the US. Of course, it's not monsoon style of weather system, but they got 583 millimeters in a day. That's half the yearly average in one day. And so you see enormous flooding. 2 years ago in Houston, Texas, they got 1,500 millimeters of rain in 3 days. Why so much water? Because the air is hotter. It contains more vapor. When the vapor condenses, falls down as rain, you get huge amounts of rain. And so the danger of flooding is becoming more and more evident. In Greece, 3 weeks ago, there was a big storm called Daniel. You know, they give names by the order of the alphabet, A, B, C. That was number 4, Daniel. Daniel rotated in the Mediterranean. First it hit Greece and inundated the northern parts of Greece, and then it migrated across the Mediterranean to Libya. And I'm not sure you've seen it here in the news. There was a huge disaster in Libya. Flooding was so severe that dams on the river collapsed, leading to 11,000 people dead in a Libyan city. And that's a desert country. That's part of the Sahara Desert. But that system, that storm, Daniel, we call it a Medicane, Mediterranean hurricane, becoming more frequent in the recent years because the Mediterranean itself is warmer, so it evaporates more water in summer, and because the air exponentially becomes more able to contain a lot of water, so when we finally get clouds, they are more potent, strong, and they produce much more rain. And this is, I tell my students, shape of things to come. Maybe we will have less rainy days on total, but each rainy day will have much more rain in a single day. Because when we finally have clouds, we will have much more rain because of the Clausius-Clapeyron thermodynamics equation. Exponential increase, A e to the power of minus b over t. These are constants. Empirical formula, proved and tested. And in any discussion on the repercussions of climate change, you will hear physicists tell you about climate change, about the Clausius-Clapeyron equation. More water vapor in the air. And so the basic physics is quite simple. Air heated by the sun starts rising motion because of lower density, so it goes up, reaches a certain altitude where the temperature is low enough such that water starts to condense on those solid aerosol particles which I mentioned. Be it smoke, be it minerals, be it dust, pollution, or biological origin condensation nuclei. And LCL means the lifting condensation level. And you will notice that artists always got it right because they draw the clouds like with the base in a certain line, almost a straight line. This is the altitude where the temperature is low enough for the air to saturate and condense on the aerosols. So you can see this is the cloud base lifting condensation level, and then starts to grow like a cauliflower or a popcorn. My daughters used to call them popcorn clouds. Like you see them. If you take a picture in fast motion, you can actually see the cloud mushrooming and growing. Some clouds are effective in producing rain, and some are what we call fair weather clouds. They just hover and then re-evaporate and are gone. And how do we measure? As I said, we fly into those clouds with airplanes or nowadays with drones. But when I was doing my PhD in the 1990s, Tel Aviv University, we did that. So you see, these are devices which you put under the wing of an airplane, and they actually, you shoot a laser beam from one point to the other. You have a mirror that receives the laser, and what you actually document is the shadow of the particles that are in the air below the wing of the airplane. It looks like this, okay? Very small airplane. Actually, I confess, it was very scary, but you have to be brave, because you fly into a cloud, and the cloud is, you have this motion and turbulence, and because the air is rising, it's not always pleasant. Some of my colleagues throw up. It's really, really hard. But that's part of being a student. You have to suffer. So we had those instruments under the wing. We fly into the clouds. We measure the concentration of water, the temperature, the humidity, and the shape of the drops. And this is how you see them. This is water drops. It's actually the shadow of the drop. So this is the time, and every strip is 1 second. You can see the time is here. And this is we can actually measure the size and see if this is a raindrop, a cloud drop. And when we go higher up, when the temperature is much below zero, we start seeing crystals, ice crystals. You can see snow crystals. So it's water drops, and then it becomes ice. And ice is the secret to make lightning. Without ice, most likely we would not have electricity, but I'll come back to that tomorrow. So when eventually precipitation forms in the cloud, it falls down. A raindrop usually falls 1 meter or half a meter per second, not very fast. There's a terminal fall speed because the air puts resistance, a hydropower that stops the terminal fall speed of the droplet. And then if you have soft hail or large hail, it can reach much, much faster. They can be really fast and really massive. In big storms, you can really find really heavy hailstones, and they usually accompany lightning, tornadoes, and severe, severe weather. I'm not sure you've seen such huge hail in Mumbai, but in other parts of India, I know there are records of massive hail in certain specific storms. So how do raindrops grow? They grow mostly by diffusion. Water vapor keeps condensing, but this is not a very effective process. It takes a long time. The most effective way is collection by collisions between droplets. Big drops swallow small drops, grow bigger, swallow more drops, and then they grow big enough that they can fall down against the upward motion of the air and fall down to the air. So we can write an equation. I don't want to bore you with the details, but we know that nature produces this very effectively, and the idea to enhance rain is to help Mother Nature be a little bit more effective. That was the philosophy, and still is. That we know that precipitation forms either in warm clouds when there is no ice, so it's collision coalescence, or when you have ice, then ice collects and freezes and then melts and falls down as rain. So the idea between the scientist was, maybe we should find a way to enhance the amount of rain and the effectiveness of the rain producing process. So, to be honest, I'm not sure there is an answer yet as to the effectiveness of rain enhancement. But many countries are coming back, as I said, to the idea, because maybe the best way to do it was to enhance the amount of ice. So we will put ice either in the form of ice nuclei or dry ice, cool the clouds and make it even more ice abundant, and by this we will increase the amount of ice. Ice will coagulate, create snow, snow will fall down, melt below cloud base back into liquid and fall as rain into the ground. So it's still out there. I can tell you it used to be like career death. If you choose as a PhD to work on cloud seeding, people would say, not interesting. But now, because of climate change and because we have different ideas and different methods of doing things we did in the 1960s and 70s, people are slowly coming back to the idea that we can play with clouds, we can play with the shape of ice in the cloud, we can geoengineer the planet. To be honest, I'm not absolutely sure that it's a good idea, maybe on a local scale, but certainly not on a global scale. Don't play with the clouds of an entire planet. Maybe if you want to enhance rain in a place that is needing this additional water, you can maybe do some cloud seeding. But if you want to play with massive systems, don't try it. And rain can be very different in types and in shape. This is something you don't see in tropical countries like India, but in northern countries, sometimes the rain, when it hits the ground, freezes instantly, becomes ice on impact. And we call this freezing rain. So it falls down as water, and when it reaches the ground, because the ground is below zero, it immediately freezes, and so becomes a freezing rain. You can see that these are cherries actually frozen solid into the rain that came down from the earth. And one of the typical shapes, that you may have seen this here as well, is that rain does not fall everywhere. It usually condenses and concentrates in certain parts of the clouds, creating what we call the rain shaft, like a shaft where the rain is the most strongest, and outside of the shaft, no rain at all. It's just concentrated. It moves with the cloud, because clouds are not stationary, but it's kind of limited to a couple of miles, and not everywhere. So this is the typical convective rain. It looks like this sometimes. See, this is very strong rain coming, and actually this is a very dangerous phenomena to aviation, because you don't want airplanes to fly below such a rain shaft. And there were some really horrendous air accidents in the 1980s because pilots did not know of this phenomena of the downdraft, of this amount of air being swept by the rain, creating those winds that impinge on the ground, and there was a need to alert airplanes when this phenomena occurs. This is why most modern airports have what we call Doppler radar. to monitor and map those vertical motions of air and of rain in order to divert airplanes. If there is something like this near an airport, you should not try and attempt landing. It's too dangerous. There was an accident not last week. I think it was in Mexico. And they did not pay attention that there was a downwind from the cloud during heavy rain, and they crashed. And everybody died. Still happening today, mostly in places where you don't have radar. So, let me sum up this part. Clouds are beautiful. There's a series of stamps. If you want, you can join the Cloud Appreciation Society. I'm not joking. You can look it up on the web. There's a British society for people who love clouds. They have a book, A Cloud a Day, like they published each day of the year a beautiful picture of a cloud. So people love clouds. I think nature would be boring without clouds. And they are essential to life on Earth. Without clouds, there will be no water cycle and there will be no life. And of course, as I said, they regulate the temperature of the planet. Okay, so that was the introduction for the actual course that we will begin after the break. And if you have any questions, do ask me now. I know maybe some of you think it's really basic, but I hope, coming from various disciplines, it was important for me to benchmark that we know what we talk about when we talk about the atmosphere. To most of you, probably this is something new. So I guess if you have questions or if you want specific kind of enhancement on specific topics, just ask me now and let me know, okay? And I suppose we can break now for lunch, and we will be back 1:15 maybe? How long is usual lunch break? 1 hour? An hour. So maybe we will meet at 1, okay? So 1 hour, 15 minutes. Will be okay? Yes? Okay. Okay, so enjoy your lunch, and we'll meet back at 1, okay?